Right. Yeah, we found some very good open source hardware solutions to that type of equipment, and I think it can become much more accessible to the community at much lower cost.
Okay, thank you very much. And are you planning on eventually contaminating steel plates, because it looks like stainless steel plates? Are you planning on intentionally contaminating?
Yes, that would be the next step. I mean, we hope to see something without having to do that, just for safety purposes, lab safety. But if we don't see anything without contamination, we'd like to we consider to contaminate them. Put some maybe have a copper plate with mercury in the surface.
Yeah, the bottom would be on the surface tension of mercury. You have to lower it down as much as possible.
Right.
Okay, time's up. Next speaker. So next speaker is Professor Soyama from Tohoku University. He will be speaking on spectroscopy analysis of laser abrasion and laser cavitation induced by pulse laser.
Thank you, Mr. Chairman. Today I'd like to talk about laser cavitation. Before the laser, I'd like to talk about another cavitation. So because as you know, the cavitation is a phase change phenomenon from liquid to vapor. At the high speed and the low speed region, the cavitation occurs at the low pressure region and then collapsing. At the bubble collapsing, as we know, we can get the hot spots. So we can use these hot spots for a kind of reactor. So in just my opinion, the ultrasonic cavitation, there's a lot of researchers doing using ultrasonic cavitation. The vibration causes the cavitation bubbles. Just in my opinion, we can use the more aggressive cavitation using our water flow. So I call that hydrodynamic cavitation. So if the water passing through the narrow region, we can get the cavitation bubbles. In viewpoint of material treatment at the same power, at the electric power, we can get a more intense cavitation bubble comparing with the ultrasonic cavitation. So, of course, we must optimize flow pattern and the cavitating condition. Today, I'd like to talk about the cavitation bubble caused by pulse laser. Before that, I just introduced the hydrodynamic cavitation. This is a drawing, and this is a picture taken by myself. If we put the high-speed water jet into water, we can get the vortex. You can see white strings here. So at the vortex core, we can get the low pressure region. This is why we can get the cavitation bubble at the, and this is the high-speed water jet into our water. So we can get the cavitation bubbles. And if we put the target, the cavitation bubbles combine the big cloud cavitation, and then cavitation cloud hits the target and spread out and then collapsing. So if we take a picture by using a normal CCD camera with flash lamp, we can get the cavitation cloud. However, if we take a EMCCD camera, we can get the luminescent spot like this. Actually, this cavitation cloud is hitting about 100 Hz or several kilohertz. It's a kind of shading. And you can see a spot. So if we expose 200 milliseconds, we can get several spots here. And if we get the spectrum, if we measure the spectrum using hydrodynamic cavitation, of course, it depends on the dissolved gases. You know, if we put some argon and xenon, the luminescence is more intense. But air, we can also get the luminescence spot here. In this case, I didn't put the argon, but just normal air. But we can see some spot. And if we use a venturi tube like this, we can get a cavitation bubble here. Of course, in this case, also we can get luminescence. Now, I'd like to talk about why I'm going to move the pulse laser. As I told you, these white bubbles is shedding periodically. This is a picture taken by high-speed video camera. Cloud is shedding periodically. And if we measure the cavitation intensity, this is the intensity and this is the frequency of cavitation impact. The cloud shedding is about several hertz or several kilohertz. However, more or aggressive cavitation occurs only 1 time per second. It's very few. So I don't know why. So I'd like to make sure more precise cavitation observation. This is why I'm going to do a single bubble. And another problem, you know, in just my opinion, this sort of cavitation, this cavitation consists of small, tiny bubbles. So just my opinion, and this sort of very strange cavitation is more intense compared with the spherical bubble. So, but this is too complicated. So this is why I'd like to create more simple cavitation. But I'd like to enhance the cavitation aggressivity. So I put the pulse laser and the submerged pulse laser to the target. So this is our experimental setup. I use the green laser, and the pulse width is about 5 nanoseconds. And the laser energy is 200 millijoule. So I put the target is titanium, nickel, and other metallic materials. We observe the cavitation phenomenon by using the high-speed video camera. And also, in order to get the spectroscopy, a time-resolved intensifier in this point CCD camera was used. So this is our observation by using a high-speed video camera. You can see a shock wave here. The pulse laser here is water. The pulse laser was hit to the target. So you can see a shock wave and propagate. After that, the bubble is developing and then collapsing. At bubble collapsing, we can get another shock wave. So I'd like to show the video. Maybe it's very quickly, possible. And more, little bit too slowly, you can see a shock wave. And the bubble collapsing is shrinking, and maybe you can see some shock wave. Actually, this is a kind of normal. Now I'd like to show the shock wave into the material. In this case, I use the photoelectricity. So I put the clear acrylic resin in the water. So bubble developing and collapsing. You can see some black and white pattern. So this is a propagation of the shock wave in the material. But this is in this case I use a clear acrylic resin because of photoelasticity. And the bubble collapsing, and you can get the shock wave. show some results by measuring the PVDF film. I'd like to show the impact in the materials. I put the special sensor in the target. And this is a signal from the hydrophone. Hydrophone was put in the chamber. And also I put another submerged shock wave sensor in the chamber. If we measure the shock wave in the material by using the sensor, this is the aspect of bubble. We can get the abrasion, so we can get some signal. After that, bubble is developing and collapsing. So we can get the impact here. And also the bubble is rebounded. So secondary collapsing, we also get another impact here. So this is a signal from in the material. If we put the hydrophone in the chamber, we can get the laser abrasion and the impact caused by cavitation bubble collapsing. If we measure the pulse height or intensity of bubble collapsing changing with the bubble size, so this is the intensity of bubble collapsing, plotting with developing time of bubble. Actually, I changed the laser power so we can control the bubble size. The peak value of intensity is proportional to the developing time of bubble. But if we measure the elastic deformation, this is a kind of elastic deformation of the material, and this is the developing time of bubble. Actually, the developing time of bubble is proportional to the bubble diameter. So the plastic deformation of material is a kind of proportional to the volume of bubbles. So if we create a big bubble, we can get a big intensity. Anyway, I'd like to show some results of spectrum. In this case, I just measure the spectrum just after the laser abrasion. If we change the material, of course the intensity is different. In case of titanium, we can get more intense luminescence or just abrasion. Just abrasion. If we change the material, the intensity is changing. But this is a wavelength and this is intensity. Titanium is more intense. So now I'm very interested about the spectrum and bubble collapsing. So airline, after 300 microseconds of the abrasion, so the bubble is developing and collapsing. So around here, still we can get some intensity. And 300 microseconds, 400 microseconds. At this condition, the bubble developing and collapsing time is about 1 millisecond. So still we can get a very large intensity of some light. And then decreasing and decreasing. So actually I expect the bubble collapsing, we get another luminescence. However, it is not obvious because this is the target of titanium. So you can see the oxide titanium, it's a black one. So this is the composite of titanium, oxide titanium. So I just my opinion, the oxidation causes some luminescence. So this is why two strong luminescences occurred at this region. Now I'd like to summarize our studies. So the impact induced by laser cavitation is 1.5 times larger than the laser abrasion. So we must optimize and we must think about cavitation power. That is important. And the shock rays in the material caused by the pulse laser were observed. And the spectral analysis of laser abrasion and the laser cavitation induced by pulse laser can be applied using a time intensifier. Actually, we call that the ICCD with the spectrograph. The luminescence caused by oxidation was particularly large in the present experiment. Thank you for your kind attention.
Thank you for your presentation. Now, floor is open for question and discussion. Any questions? Please.
Several years before, Professor Arata used laser, CO2 laser, to stimulate cold fusion with nanomaterials. You think there are some correlation about?
You mean
He used the CO2 laser, very high power CO2 laser. I don't know if you know such kind of paper from Professor Arata.
Sure.
No, okay.
I know the Professor Arata, but
Yes, such paper, no. Okay, we will send you.
okay, thank you.
Any other questions? We have much time. So you are doing some kind of laser abrasion in the liquid, so you have tiny particles in the.
Yeah. Actually, in case of tiny particles, the sometimes is very problem because if we treat it or experiment the tiny particle is blocks the path of the laser, so the filament is decreasing. So we must consider about the particle just a contamination. We must reduce the contamination.
So you said how deep the target is in the liquid?
We put just target and during the spectroscopy analysis, we're just moving the very steady speed. And we must put some